Good morning. My name is Reza Nejabati. I am from University of Essex, Department of Electronic System Engineering. In our research group, we are working on optical packet switching technology. And my presentation today is class-based traffic aggregation in optical packet switch WDM networks. This project is supported by ESVRC through the OPROM project. The goal of the OPROM project is design architecture and demonstrator for edge-to-edge optical packet switching with all core node, with all optical core node. And this project has an industrial partner, which is Marconi. Topics that I am going to cover in my presentation today are, at first, a brief overview on optical packet switching and its benefit. Then I am going to explain the network scenario, which is using optical packet switching. And afterwards, I will explain the functionality of the edge router in optical packet switch network. And then I will explain a novel optical packet assembly and traffic aggregation method for the edge optical packet switch router. And afterwards, I will explain that how we can use this optical packet assembly mechanism to shape our traffic in suitable form for the core network, as well as to provide the mechanism for our optical core to offer quality of service. And at the end, I will explain hardware architecture and realization method for our edge router, especially in opto-electronic parts. Why optical packet switching and why we would like to use optical packet switching? The one important key benefit of optical packet switching is spectral efficiency. The future traffic is a multi-service traffic, which is a combination of data, voice, and video. This kind of traffic is bursty in nature, and we have a peak of transmission occasionally. And also, the future network will be based on IP traffic, and IP traffic is burst in nature. If we want to use the circuit switching in wavelength domain, we must always consider maximum bandwidth to be able to cope with the peak of traffic transmission. But with packet switching, it is possible to allocate bandwidth per packet demand. And also, with optical packet switching, it is possible to improve our network infrastructure cost, and because, for example, we will have a smaller optical cross connect, and so we will have a cost reduction. And also, another important benefit is the granularity of the switching. The circuit, in optical circuit switching, we will have a wavelength, maximum granularity as wavelength. But in optical packet switching, we will have a finer granularity at packet level, optical packet level. And the other thing is, because optical packet switching is using packet switching technology, in nature it is compatible with the traditional electronic packet switch, and so we can use the integrated control and management plan, for example, MPLS in electronic domain and MP lambda S in optical domain or GMPLS. Here is an optical packet switching scenario, network scenario. Can I have a pointer?
Yes. You push this.
Okay. In this network, we will have a two level of switching. One is slow switching at wavelength level, which will cover our traditional traffic, and the other thing is fast switching at packet level. This network will introduce bandwidth partitioning. Some of the wavelengths are allocated to our circuit switch traffic, and the remaining bandwidth are allocated to our packet switch. This network, to be able to support the optical to packet switch technology, it needs to have an interface with the packet switch electronic domain. So the edge optical packet switch router has this functionality. This edge optical packet switch router will use the Opto-Electronic technology, and it performs aggregation, classification, packetization, and bitrate adaptation, and also it can perform the classification to support quality of service. And in our optical core, which use all optical technology, it performs the label swapping or header swapping, space switching, and contention resolution by using the optical resources, by considering the quality of service, and also regeneration. The focus of my presentation is in functionality of edge optical packet switch router. Edge optical packet switch router has an interface functionality between optical and electronic domain different granularity. In electronic domain, from the physical layer, for example, the gigabit Ethernet, to the network layer, for example, IP, and in optical domain, from the optical packet level up to wavelength level. And also, it needs to have an understanding of the control layer in both domains. For example, MPLS, as I mentioned, and MP lambda S. Okay. Our optical packet switch has an input and output interface to the optical core, optical transport network, will be positioned at the add and drop port of the optical cross-connect. As an input port, it accepts the electronic packet data through the internet service provider and label switch router, and map them to the optical packet and transmit to the optical transport network. At the output port, it accepts optical packets, segregate them to the label packet, and transmit them to the label switch router and internet service provider. Optical packet switch, edge optical packet switch router, as an input node, provide the aggregation mechanism to offer class of the service, to make optical packets, and also to bring traffic shaping with this aggregation method for the core network. Here is just abstract functionality of the optical packet switch router as an edge node. The first part of, or input part of, it is like a traditional gigabit router, which has an input interface with the physical interface functionality with physical layer, like gigabit Ethernet. And then it has a forwarding and routing engine and the classification and routing table. After forwarding the label packet to the appropriate output port, in each output port, we will have our classification and optical packet assembly mechanism. Each optical packet will be classified into the separate aggregation buffer based on the class of a service and destination address in each output port of the router. And then aggregated packets are scheduled for transmission based on their priority and, again, class of the service. Prior to transmission, our scheduler sends the suitable control data for wavelength assignment part and our header insertion to insert the header in front of the packet, optical header in front of the packet, and also to allocate a suitable wavelength per packet. And why packet aggregation? We would like to use the packet aggregation at the edge of the network because we can reduce the number of entities that must be processed in the optical packet switch in the core, all optical packet switch in the core. And also, we want to use the packet aggregation to classify packet with the same class in same optical packet and same destination address, and also to be able to shape the traffic for the core. Packets in edge are aggregated based on the two parameters. One is destination address, and the other is class of a service. And also, aggregated packets are scheduled for transmission based on the maximum experience delay in the aggregation mechanism for each packet, and also for a maximum number of bytes per optical packet, which means we consider optical packet to be transmitted to a specific destination and for a specific class of a service, And this optical packet in the edge can experience a maximum limitation, a maximum limit of the delay, and it can have also a maximum number of bytes. This aggregation method has a direct impact on the traffic characteristic. It has an effect on the degree of the self-similarity and burstiness of the traffic, and also in the correlation of the traffic. And we can use this aggregation mechanism to reduce the burstiness of the traffic, self-similarity of the traffic, and make the traffic for the core more predictable. So if a traffic is predictable for the core and it is smooth, so the core packet drop in congestion period at the core will be reduced. We have proposed here an aggregation algorithm. We try to find the aggregation algorithm based on increasing the probability of the optical packet transmission with same size and with the same experience delay. To do that, we have defined two aggregation, let's say two aggregation threshold parameter for each main aggregation parameter. For example, one of aggregation parameter are number of packets per optical, number of bytes per optical packet. We have defined a low threshold and high threshold for this number of byte per optical packet. And also the other parameter is maximum experience delay in each each aggregation buffer for optical packet construction. We defined again low-level threshold and high-level threshold, which is TL and TH here. And this four parameter has defined a trigger zone in the aggregation parameter area. We try to define this parameter such that we can increase with our aggregation algorithm the launching optical packet to the optical transport network when they are in this zone. We have simulated our algorithm to see what is the effect of this aggregation algorithm on the traffic parameters. For our simulation, we have used 20 gigabit router as an input with 1 gigabit per second each link, and 2 destination address, each destination address with 3 classes of a service. And we have used the bursty traffic model as an input with 0.8 hertz parameter, which is quite bursty traffic. And our class of a service and destination address are selected randomly with uniform random distribution for each packet. Here is some result. At first, I need to explain that the maximum length of or maximum number of bytes per optical packet are defined by our aggregation buffer. For example, if you have an aggregation of 1,500 bytes, it means the maximum optical packet will be 1,500 bytes, the content of the maximum content of the optical packet. So we simulate our design with two sizes of the aggregation buffer. One is 1,500 bytes, which is compatible with the Ethernet packet in the electronic domain, and the other with 3,000 bytes. And we consider 4 set of aggregation parameters, or 4 set of the trigger zone. But the first one is equal to just a simple aggregation without considering any window, because it is just one parameter in each domain. We can see we got a good result. We can see especially for large buffer size, when we want to generate optical packets with large size. If we use this window aggregation, we reduce our experience delay significantly. And also, we can reduce the experience delay with a small size, but not as much as with large size optical packets. But now we want to see what is the effect of this algorithm. It is good in terms of the experience delay. But what is the effect which is very important, the effect of the burstiness of generated traffic for optical domain. 2 parameters define the burstiness of traffic. One is hertz parameter, and the other is traffic correlation. We measure all of this in our simulation for both buffer size with our aggregation traffic algorithm. We can see, especially for window size 3 or trigger zone 3, we got a good result in our burstiness reduction. From 0.8 at the input, we reached a 0.5 almost, which is almost a smooth traffic. And also for traffic correlation, we can see our correlation goes to 0 very fast for a small buffer size. But the diagram with the plus signs, it's the input correlation, which is it doesn't go to 0, which is a bursty traffic, but it goes to 0 when it's aggregated in our with aggregation. And here is again for 3000 bytes it goes to 0. But for Windows size 2 or 3, 4, which will have a good experience delay and a good Hertz parameter reduction, we'll have a fluctuation in the especially for short term and a small time lag in traffic. Okay, now this last part of my presentation, which is the hardware implementation of functionality of the edge optical packet switch router in optoelectronic domain. Fast tunable laser and fast reconfigurable hardware or fast FPGA are suitable platform for implementing this functionality which is required for edge optical packet switch router. Here is the architecture of our demonstrator. We use the fast FPGA from the Xilinx. This FPGA can offer us a serial input and output port at 2.5 gigabit per second at the moment, but in near future they will promise us 10 gigabit per second serial in electronic domain, which is quite good. And we connect to the Ethernet link here, and we use the internal hardware resources to define a routing table just to route the packets for 3 classes of a service and 1 destination address, which is very limited demonstrator. And then we use the embedded processor of this FPGA to perform our aggregation algorithm, and we transmit them through the 2.5 gigabit per second link at the moment that we have. Then we use the MUX to reach 10 gigabit per second. And then to assign the wavelength per packet, we use the fast tunable laser. We managed to get a very good result from the fast tunable reset. We use the GCSR laser, which is grating assisted co-directional coupler with sample grating laser. It has a good tuning range around 50 nanometers, so we can tune the wavelength emission of this laser by controlling current of reflector and coupler. We managed to precisely control this current through FPGA and D2A converter, and we reached the tuning times of less than 8 nanoseconds, but we hope by improving our electronic very soon we can reach less than 4 nanosecond tuning time. Here is our aggregation demonstrator and the whole architecture with the tunable laser, and is some result from this here. We managed to generate 4 packets with header in front of us, in front of each one with in 4 different wavelengths. And if we use the filter, after we use the filter and after pin, we got this result, which is the header and the packet, and quite good. They have a distortion and overshoot here, but for first result they are good. And at the end, my conclusion is I explained that the optical packet switching, full optical packet switching, is very attractive alternative for implementing future IP network over WDM network. And also, I showed that we can use traffic aggregation to have a good performance for our core and to provide quality of service as well, and also to shape the traffic to increase the performance of the core again. And also, we showed that our aggregation parameter improved the experience delay as well as the traffic characteristic of the network. And also, we showed that by using the fast tunable laser and fast reconfigure hardware, it is possible to, at the moment with current technology, to implement for higher speed optoelectronic functionality which is required for edge optical packet switch router. Thank you very much for your attention.
Thank you. There's time for one question.
I have a question. Do you assume to use erbium-doped fiber amplifiers or Raman amplifiers in your network?
For our, let's see.
Well, the question continues. If yes, how would you overcome the burstiness or the cross-gain saturation effects in the amplifier?
I will explain. In the edge of the network, which is the connection between electron and optical domain, actually, I personally, I don't use the erbium dot amplifier for my part, because just I generated for the optical domain. But this is another project called OpsNet that they are in our university, that they are demonstrating the full optical packet switch core. They use the erbium doped amplifier, but I don't know how they can compensate that this impairment. But they managed to demonstrate the packet switching in optical core.
Okay.
Okay, thank you again. I think this showed that there is a lot to be done, I think, still in optical packet switching, but it's good that there is progress. Thanks again,
Thank you.
Reza.